Alright, so just to start off then, because I got a lot of questions regarding this, I thought I would go and clear up a couple of concepts regarding Laplace transforms. Firstly then, starting with the definition of a Laplace transform, it's given by this integral here. So for a function y of t, where t is time, the Laplace transform of that function is given by this improper integral here with this exponential function, and this tells us where those common Laplace transforms, the ones that appear in the tables, come from. So there are a few notes on this in our textbook, Appendix A, A4. There's a list of properties of Laplace transforms, in particular property number 2 that talks about the Laplace transforms of increasing derivatives of the function y of t, and then also there is a reasonably short table of common Laplace transforms given in table A.4.1. So going back then to our definition of what a Laplace transform is, just to show you where a couple of those common results from the table comes from, well, it comes from solving this improper integral, replacing the function y of t. So if y of t is just a constant 1, then we have this improper integral of e to the negative st. We integrate that with respect to t to get this. Obviously we do 1 over the power, it's an exponential function, so the power stays the same. We evaluate that at infinity, and if t goes to infinity here, so it's more mathematically correct here to basically replace the variable t with something else and then consider what happens to that variable at the limit, or as that variable approaches infinity. But just for neatness here, we're just going to assume t goes to infinity. That makes this exponential function go to 0, and therefore evaluating the same thing when t is 0, this whole expression is going to go to 1, so we're just going to be left with negative 1 over s. So that just reduces down to 1 over s. And that's what you can see is the result in the table here. If y of t is 1, then y of s, or the Laplace transform of 1, is just 1 over s. So extending that out a little bit further, let's just do the next one in the list, the Laplace transform of the function t. We replace y of t here with just t, right? Now we have to solve this integral using integration by parts. Hopefully you can remember how to do that. We use this formula here, so the integral of u v dash, where dash denotes the derivative with respect to t in our case. That's given by u multiplied by v minus the integral of u dash v. So we choose u and v to be convenient to us so that we can work out what the derivatives of those are. So we choose v dash in this case to be e to the negative st, so that to find v we just integrate this, and that's similar to what we saw above here, right? And then we let u to be just equal to t, and obviously just differentiating that with respect to t gives 1. So we plug in v dash and u dash into this formula here, and essentially split up this integral that we started with. So we get this expression here. All I've done from this step to this step is just taken out the 1 over s, because it doesn't depend on t, to the front of the integral to get this. And this is what we saw above when we were evaluating the Laplace transform of 1, right? So we do the same thing again. We evaluate this expression as t tends to infinity. That's going to make this part go to 0, and it's going to make this part go to 0 as well, right? And then we evaluate the same thing as when t equals 0. So that's going to make this part 0, and this exponential function 1. So this will just go to 1 over s squared. And again, we can go over to our table, check if y of t equals t, the Laplace transform of that is 1 over s squared, which is what we've just derived. So all of those are contained in this table, or the most common ones are contained in this table. And now we're just going to do an example of how to actually apply that and solve an ordinary differential equation using Laplace transforms. Alright, so as our example, we're going to have a look at solving this initial value problem. This ordinary differential equation here, second order, we've got some initial conditions. So we're going to solve this differential equation by applying the Laplace transform method. The first thing we do is go ahead and apply the Laplace transform to each of the terms of this equation. You can see I've taken out the constants to the front, as they don't affect our Laplace transform. And then we have to evaluate or look up from our properties and tables what these individual terms are. So the Laplace transforms of the various derivatives of our function y, and then also we'll have to look up the Laplace transform of this function here. So these first ones are just generic properties of the Laplace transforms of the various derivatives of y. We can look those up in our properties table. So this is from properties number 2 in the textbook, specifically here where it defines the various Laplace transforms of the derivatives of our function y, so y dash, y double dash, and y triple dash. And you can see these depend on our initial conditions. So what I've done is gone ahead and applied our initial conditions that we were given in the question statement to those expressions to get this. This Laplace transform we're going to have to look up from our tables. So we're going to need to find something in the tables that corresponds to this expression here. So again, we take a look at the appendix from our textbook. We can see this table of common results and functions. So we're going to be looking at something that looks like t e to the negative 2t. So we're going to look at this here, and then we're going to basically correspond our values for n, a, and also for the positive or negative sign here in the exponential function. So here, look, this is the result that I'm going to use. I've got t to the power of 1, so I'm just going to use n to be 2 here, so 2 minus 1 is 1. And then I'm going to have e to the negative 2t, so a is going to be 2. I'm going to use the negative sign here, which then corresponds to the positive sign down in here in our result. And then, of course, if n is 2, 2 minus 1 is 1 factorial, which is 1. So all of this will just be over 1, so that corresponds nicely. So the result we're going to get here is 1 over s plus 2 squared. So what we do next is go ahead and plug all of that stuff into our original equation. So that's what I've done here. Obviously remembering, of course, that I have these constants out the front. So 2 multiplied by all of this stuff, 3 multiplied by all of this, and so on. And then I end up with this expression, which I've tidied up a little bit, factorized, and then basically rearranged the whole thing for our Laplace transform function of s, f of s, which is a function of these two fractions, right? The problem that we've got now is that we need to combine these two terms so that we can apply partial fractions. So that's what's next. So these are our two fractions. What I've done is tried to rewrite this second term over the same denominator as the first term, right? I've done that by multiplying the numerator by s plus 2 squared. That allows me to write the whole expression over the same denominator. Then I've just tidied up the expression from here and then combined terms. And then because I now have a single fraction, I can use the partial fraction method, which is what I've done here. Of course, I take the various components of the numerator, separate them out. I've got a over this term, b over s plus 2, c over s plus 2 squared, and d over s plus 2 cubed. And then from the original expression, so I'm going to have this numerator here should be calculated based on these values a, b, c, and d. So a is multiplied by s plus 2 cubed to get the same denominator, right, because it's over 2s minus 1. B should be multiplied by 2s minus 1 and then s plus 2 squared to get the same denominator, and so on. And then I've collected or expanded out these terms involving s from these brackets, and then I've collected terms corresponding to s cubed, s squared, s, and then all of my constant terms. So comparing these expressions to the left-hand side, I can come up with a system of 4 equations. So there are no s cubed terms on the left, so this should be equal to 0. I have minus 4s squared on the left-hand side, so all of this stuff should be equal to minus 4, and so on. And then I've got a system of 4 equations, 4 unknowns that I can solve for a, b, c, and d. So once I have all of that, I can pull all of that together back into my expression for my partial fraction, and then I need to get this in a format where I can look up the inverse Laplace transforms to transfer this back into functions of t rather than functions of s. So I've written, well, the first thing I've done is factorized out the 1 over 125 constant, and then I've written this in terms of s plus a constant, right? So I've tried to get rid of multiples of s. I have s plus 2 here, s plus 2 squared here, and s plus 2 cubed here. And then what I do is I just go back into the tables. So now I'm looking specifically at the right-hand side to convert these functions of s back into functions of t, right? And so I'm looking at expressions of this form here. S plus 2, so the first one, this is just going to convert back into this expression or function of t, and so on. The only difference is here I might get this occurring function of t out the front of my exponential function, and then I plug all of this stuff back into this equation here to get the final form or the final solution, function of y, function of t, given as this expression here. So what have we done? So we've converted our original equation, solved it algebraically by converting it using the Laplace transforms, and then at the end we've transformed it back using the inverse Laplace transforms to get our solution as a function of t.